Hey guys, welcome to the Section 3 review video on MDPs. Let's go ahead and start by talking about the formulation of an MDP. So here on the top right, I've just added the canonical example that we show you in class. And as we talk through all of these parts of an MDP formulation, we can kind of talk about how they correspond to this example that you guys have had in class. Okay, so starting off, MDPs are going to have a set of states, S, and a set of actions. In the example here, you can think of S as maybe each one of these grids, and the actions as going up, down, left, or right. There's going to be a transition function, T, S, A, S prime, and this is going to encode the probability that you land in state S prime by being in S and taking action A. So you'll notice that this is going to be stochastic, not deterministic. So for example, from our start state here, maybe if we take the action up, we have a 90% chance of moving up, but then there's also a 10% chance that we move right, okay? And the transition function is going to encode that. Other than that, there's going to be a reward function for taking some action from a state and landing in a next state. There's going to be a value for each state, V of S, and then there's going to be a policy for each state, pi of S. So this policy is going to encode what action we want to take from state S. And then finally, it's going to be a discount factor gamma, which is going to encode how much we care about future rewards. And we'll talk more about those later. Now, the goal for any MDP is going to be to find the optimal policy. And so the algorithms that we're going to show you are going to try to come up with the policy that will maximize the expected value of each state. All right, so looking at the formulation a little more, this is what the search tree for an MDP is going to look like. So at the start, or at the top here, we'll have some state. From this state, you get to choose the action that you take. And after you take the action, you're going to land in this green node, which we'll call a Q state. Okay, so the Q state is going to depend on the state here, and then the action that you took here. All right, from this Q state, you'll then be randomly put into one of the next states, S prime. And which S prime you land into is going to be based on the transition model, right? So the transition model says the probability that you'll land in state S prime given that you're in Q state SA. And then there's also rewards in these transitions here. Okay, so maybe every time you land in some state S prime, you get a reward of +1. That's going to be encoded in the transition here. Okay, so let's talk a little bit more about the values. So again, here are the values in the Q state values, which correspond to the Q state here, or the state here. We're going to use this set of equations, also called the Bellman equations, to define the optimal values of every state. Okay, so going through this briefly, we'll call V star of S. Oh, by the way, these stars encode optimality. So V star of S is going to be the optimal value of state S. So V star of S is going to be the max over all actions of the value of the Q state, of that state and action pair. Okay, so basically from the states you get to choose an action. So we're just going to choose the best action that leads us to the Q state with the highest value. Now from the Q state, we don't get to choose the next state that we land into. It's going to be stochastic, that depends on this transition. And you'll notice that it basically behaves like an expect-to-max node, right? So we'll just take the expect-to-max value, which is going to be a weighted sum over all possible next states. So it's going to be the probability that we land in this next state times the reward of landing in that next state plus the discounted value of that next state. Okay, so here is where we see the discount factor that we talked about in the formulation. And then this third equation is no new information. It's just basically combining these first two equations. So these equations are all well and good after we have already found the optimal values, V star. But the problem is, in most cases, to find what these optimal values are, right? And to do that, we're going to use a couple of different algorithms, the first of which is value iteration. So the goal of value iteration is going to be to learn the optimal value of all the states, and then to use those optimal values to compute the best policy. And the way that we're going to do it is as follows. So we're going to start by initializing all values to 0. So we can call this subscript 0 the time step. So initially, the value of all states is set to 0. And then we're going to repeat this equation until we converge to some stable set of values. So the value of state S at the next time step is going to be the max over all actions times a weighted sum of the probability of landing in that next state times the reward plus the discounted value at the kth time step of that next state. So you'll notice that this equation looks basically like the Bellman equation that we showed you here, except instead of these stars, they're replaced by time steps, right? K plus 1 here, and then a K here. So what does it mean if we repeat this equation until we converge to some stable set of values? When we converge, what it basically is saying is that the value vk plus 1 and the values for vk don't change, right? And if they don't change, basically it means we have the optimal values. So that's how we're going to calculate the optimal values. So what are we guaranteed for value iteration? Well, we're guaranteed that if our discount factor is less than 1, remember a discount factor here, the values are guaranteed to converge to the optimal set of values. And basically the reason is that you can think of these Bellman updates as just some system of equations, right? Where you have number of state equations and number of state variables that you can tweak. So like say k is the number of states, you have k equations, k variables. There's only going to be one set of values that is going to satisfy that system of equations. And that's what this value iteration finds. Okay, another thing that we'll notice is sometimes the policy that we're going to extract from these values is going to converge faster than the values, right? So it might be the case that we don't have the optimal values for all states, but the action that we're going to end up choosing is going to be optimal. Because these policies sometimes converge faster, a better solution might be to do a search over policies rather than to try to find the optimal values. And that's exactly what policy iteration is going to do. So here, instead of trying to find the optimal values always, we're going to find the optimal policies by iterating over values and policies. Okay, so what that means is basically we're going to split up policy iteration into 2 stages. There's going to be a policy evaluation stage where we feed in a fixed policy and we find values associated with that fixed policy. And then there's going to be a policy extraction stage where we are given the values of all the states that we calculated in our policy evaluation stage. So we're given those values, and then we're going to find the best policy given those values. So here in the policy extraction stage is where we're going to change and improve our policy. All right, so let's talk a little bit more about what policy evaluation and policy extraction do. So here is policy evaluation. Again, the goal is to find values for some fixed policy, call it pi. And the procedure is going to be basically the same as what we're doing for value iteration, except we're not maxing over actions, right? Because again, we're given this fixed policy pi, all our actions are fixed. And we're going to initialize the value of all states to 0. And then we're going to do this update. So again, there's no max here, because we don't get to choose our action this time. Our action is fixed by our policy pi, but we're just going to update it based on this guy. And then we're going to repeat that until the values converge. Now, okay, again, this is very much like value iteration, except you don't get to choose your action. They're decided by pi. Now, what policy extraction does is it's going to be given a set of values of each state, and it's going to extract a policy from those values. Okay, so where do these values come from? Well, they come from what we did before in policy evaluation, right? So we're going to use these values, and then we're going to compute the policy based on those values, okay? And what that computation looks like is this. So we'll come up with some new policy, pi sub I plus 1, and then what that policy is going to be is going to be the argmax over A, the Q value for that SA. So putting both of these together, we get the full policy iteration algorithm. So we're going to keep on going until the policy converges. We're going to do one stage of evaluation. So we're going to pass in some fixed policy, and we're going to calculate the values for that policy, and then we're going to do one stage of improvement. Okay, so given those fixed values that we calculated here, we're going to get a better policy by extracting the best action from each state. And then we're just going to repeat that until our policy converges. And this typically is going to be faster than value iteration. Okay, so that's it for this week. Good luck on your homework, and I will see you guys next week.